Hello, I'm Tom Coughlin. I'm president of Coughlin Associates. Coughlin Associates does consulting, both business and technology consulting of various sorts in memory and storage technologies. I also put on various industry storage and memory events and write reports on digital storage and memory and their applications. And in fact, this presentation will be based, at least in part, on a publication on emerging memory technologies that a colleague, Jim Handy, and myself co-authored. And today I'm going to talk to you about memory and storage for artificial intelligence from the edge to the data center. First, an outline of what we're going to talk about today. We'll first get into why we need these emerging memory technologies, how these will lead to changes in the computing model. We'll meet these memories and find out about them, find out who's making these non-volatile memories, some real-life applications, and an outlook for the future before we show you some summary and references. Let's get into why we need emerging memories. There's projections of big data generation ahead. IDC is an often quoted report where they talk about 175 zettabytes of data generated annually by 2025, up from about 59 zettabytes of data that they projected were generated in 2020. Now, most of that data comes from sensors, cameras, other sources, and needs to be processed immediately for real-time decisions. That's going to drive increase to store and process this data in devices or at the network edge where you have low latency. And probably only a few percent of this data or representations of what was done with this data will end up on long-term storage. In general, we're going to see a greater use of artificial intelligence in devices at the network edge and in data centers, which will increase memory requirements. In addition to the growth of data being processed, other considerations are important. Power consumption, as well as latency and data rates, are important considerations in system designs. Now, this leads us to look at the memory technologies that are going to enable us to handle this data tsunami. The semiconductor industry is being forced to change which memory technologies are used in embedded applications like microprocessors, ASICs, and other system on chips. This is because flash memory can't scale to keep pace with CMOS logic process advances. The scaling limit was a problem with NAND flash. Planar NAND stopped scaling at 15 nanometers, with the industry is forced to adopt a 3D structure to continue to provide Moore's Law type cost reductions. System on chips used NOR flash, and NOR stopped scaling at 28 nanometers with the adoption of the FinFET. Some sort of new memory technology is needed to support these chips' code storage requirements. This is suddenly providing an opportunity for some other technology to replace NOR flash for all processes below 28 nanometers. But it's not just NOR that is headed for replacement. System on chips use SRAM to store temporary data, and this SRAM is poised to stop scaling, or at least slow dramatically, around 14 nanometers. And even DRAM, the workhorse of memory technologies, working memory, is also showing signs of slowing down in its technological advances. There will be side benefits of this change from these volatile to non-volatile memory technologies. Alternative memories not only scale past the limits of established technologies, making them cheaper to produce, but they're again persistent, and they have more balanced read and write speeds. This will impact the way systems and softwares are configured, and we're going to discuss some of these changes during this presentation. This is a chart that's used to illustrate the issue of scaling. It shows two lines that represent NOR flash and some new emerging memory technology. Process shrinks have been able to reduce costs for the entire history of the semiconductor market. The process nodes run along the bottom, shrinking as we move from the left to the right. Relative cost on the vertical scale has always declined in proportion to each process shrinks as we get more of the memory per die. But flash memory has a problem after the 28 nanometer node. NOR flash, which is the non-volatile memory that the industry uses to store code in microcontroller, ASICs, and other system on chips, stops scaling at 28 nanometers. That causes its cost declines to cease, as the red line shows, by abruptly going horizontal. Manufacturers are addressing this issue by migrating to new memory technologies, which will allow further cost reductions. These emerging memory technologies are represented by the black line on the chart. Although today they are more costly than NOR flash, their cost will inevitably fall below that of flash, since they continue to scale past 28 nanometers. SRAM has a similar issue. Its scaling slows or stops around 14 nanometers. This is a similar chart that plots a cell area for SRAM designs presented at an IEEE conference over the last few years. The cell area, which is proportional to cost, is measured on the vertical axis, and the process geometry, as with the prior chart, runs along the horizontal axis. Cell area has been shrinking to keep pace with the process, but it abruptly stops shrinking at 48 nanometers. In addition, SRAM is much larger than the persistent memory candidates. This leveling off makes SRAM a reasonable candidate to be replaced by some alternative memory technology. The emerging memory will increase the wafer cost over that of the standard CMOS logic wafer, but the die size for some chips will be smaller thanks to the fact that the emerging memory technology will consume a smaller area than an SRAM would. This will reduce the cost of these chips, making the design based on the emerging memory more economical than its SRAM-based counterpart. That's going to drive future chips to migrate to an emerging memory as an alternative to SRAM. DRAM is working memory, used in almost all electronic devices, from consumer to industry and to enterprise applications. Like many semiconductor technologies, it has become more difficult to continue the pace of lithographic shrinks and increasing transistor density than it was in past decades. This figure shows the slowing of DRAM scaling since 2007. Although there are variations in supply and demand that also impact the cost and price of DRAM, DRAM price scaling in dollars per megabyte or gigabyte declined by about 37% annually for 37 years, until slowing to about 8% annually starting in 2008. The scaling limits for NOR flash, SRAM, and DRAM will cause memory to take up more space as logic shrinks unless we move to some new memory technology. So let's look at how these changes in memory technology will also change the way in which we do computing. Today there's a lot of excitement about using emerging memory in standard computing systems. Not only is an emerging memory attractive as a new layer in the memory storage hierarchy, but it also provides a path to interesting architectural innovations. In particular, innovations that solve data motion issues. Since a von Neumann computer, lots of energy and time are wasted moving data around. These energy and time issues can be addressed by moving from a von Neumann architecture, as is illustrated on the left, to a memory-centric approach, as is illustrated on the right. This has led to new protocols like OpenCAPI, CXL, C6, and Gen Z. These approaches support memory disaggregation by removing some memory from behind the processor, memory pooling and sharing to more efficiently use storage and memory to address new problem classes, and heterogeneous computing, which allows data to be processed by a variety of types of accelerators, which can be located close to memory. Note that the memory-centric system includes a DRAM connected directly to the CPU as near memory, low latency, and the far memory at the center of the diagram, which is labeled SCM memory, which stands for storage class memory. Since the far memory is shared, its data path to the CPU must be arbitrated, and this adds latency. So we're calling this a far memory in contrast to the near memory directly connected to the processor. The industry is slowly converging on a preferred mix of these solutions for far memory to solve today's and tomorrow's problems. Let's take a closer look at one of these. CXL is backed by a big consortium and will be a switched memory channel enabling pooling of different types of memory, various latencies and data rates, within the storage boxes. It supports memory and accelerators for resource pooling and aggregation. And there also seems to be an informal alliance between CXL and Gen Z. The Gen Z might be used for connecting these storage boxes together or the racks together as well. So these are some of the things that may change in terms of computing architectures. Now let's meet these memories. There are many emerging memory types vying to replace NOR flash. All share the same attributes. They all have a small, single-element bit cell that promises to scale smaller than the current technologies in order to support small, inexpensive die and 3D stacking. They also promise to be easier to use than flash memory by supporting write-in-place with no need for a block erase, and they have more symmetrical read and write speeds. Finally, they are all non-volatile or persistent. Data doesn't disappear when power is lost. They can all be used as persistent memory. New memories are necessary for Moore's law scaling to continue. These technologies include ferroelectric RAM, magnetic RAM, that is random access memory, resistive RAM, and phase change memories such as Intel's and Micron's 3D XPoint or Optane memory. MRAM has been shipping, but in smaller volumes. Over the history of the technology, Everspin has shipped over 120 million standalone MRAM chips, and they're the company that has shipped the most standalone chips. They have a partnership with GlobalFoundries, who's building 300 millimeter wafers for Everspin's use, but it also is offering MRAM to other customers for embedded memory applications and system on chips. We've listed some high-profile applications for the Everspin MRAM chips. Another company, Renesas, is shipping an MRAM chip that it inherited through its acquisition of IDT. Other foundries now offer an MRAM option to their system-on-chip clients, including GlobalFoundries, as we mentioned, TSMC, Samsung, and UMC. Phase change memory, or PCM, is another technology that is shipping in volume. The most widely known rendition of this is Intel's Optane memory, formerly known as 3D XPoint, which it ships in solid-state drives as well as in DIMMs. It is built on a technology that has been in development for many years. Intel's first Optane SSDs shipped in 2017, and the first DIMMs shipped at the end of the following year. Both are currently used in storage systems and other computing applications. Intel has been using Micron Technology as its manufacturing partner for this technology, but Micron has decided to exit this business and has sold the plant that was using to make 3D XPoint. Intel, Micron, and Samsung all tried to sell phase change memory chips into the standalone NOR flash market over a decade ago, but that market never developed. ST Microelectronics produces PCM-based microcontrollers for automotive applications. Resistive RAM, our third technology, is also in production, but in a very quiet way. It has been shipping by Adesto, now part of Dialog Semiconductor, since 2013. Dialog plans to license its CVRAM memory technology to GlobalFoundries to be offered as an embedded non-volatile memory option on its 22FDX platform, as well as future platforms. ARM announced a spin-out of Surfy Labs to develop and license new types of non-volatile memories based upon correlated electron materials, CERAM, in a joint development project with Symmetrix Corporation. Other companies currently ship resistive RAM into both commercial and military aerospace applications, and leading foundries are supporting RRAM as another alternative to embedded NOR flash. Finally, we come to the oldest emerging memory technology, ferroelectric memories, or SRAM. Surprisingly enough, this technology predates the development of the integrated circuit. The photo on this slide, published by Bell Labs in 1955 and shown in an edition of Scientific American that year, shows a single SBT crystal with vertical and horizontal metal traces that could be used as a non-volatile memory. From the perspective of unit shipments, SRAM has also shipped more than any other emerging memory technologies combined, having found its way into over 4 billion chips. It's most commonly used in RFID cards thanks to its extraordinarily low write energy requirements. Until recently, SRAMs are based on unfriendly materials such as lead and bismuth that most fab managers resisted putting into their factories. But in 2011, NAB in Dresden found that a crystalline form of hafnium oxide has strong ferroelectric properties. This has created new life for ferroelectric memory. Hafnium oxide is commonly used as a high-K dielectric in leading-edge CMOS processes. Fab managers understand how to make it in high volumes. Besides its use in ferroelectric memories, this form of hafnium oxide is being investigated for DRAM. Researchers have used it to produce a 3D DRAM, similar in process to standard 3D NAND flash. Let's look at who's making these embedded non-volatile memories. Leading foundries, those with processes finer than 28 nanometers, now offer emerging memory technologies to their customers. Again, as mentioned before, these include TSMC, Samsung, GlobalFoundries, and UMC. These companies offer spin tunnel torque, or STT MRAM today, and plan to offer spin orbit torque, or SOT MRAM, and other memory technologies that are faster and use less energy in the future. Although today's products aim to replace embedded NOR flash, newer technologies could compete against SRAM and possibly DRAM. Other technologies are offering resistive RAM and ferroelectric RAM today. TSMC, the largest semiconductor fab in the world, is offering eMRAM and E-resistive RAM as low-density configuration memories at the 22 nanometer node. At its 16 nanometer node, TSMC is developing an MRAM product to replace SRAM in system on chips. This is scheduled to be available towards the end of 2022. High endurance non-volatile memory will allow less data movement, support higher performance, and provide more memory on a fixed chip size, all of which are important for AI inference applications. It also enables more power-off states for power-constrained applications. Let's look at some real-life applications for these emerging memories. This is a block diagram of Ambic's 4th generation Apollo system on chip, which serves as both an application processor and a coprocessor for ultra-low power battery-operated Internet of Things endpoint devices. If you look at the lower left corner, you will see that the system memory subsystem, which is made up of MRAM and SRAM, and in fact, the chip pairs a 2 megabyte MRAM with a 1 megabyte SRAM. MRAM is also being used in Sony's GPS receiver, which can be found on Huawei's GT2 smartwatch. Built on Samsung's 28 nanometer FD SOI process, this IoT endpoint includes 8 megabits of embedded MRAM. There are many other emerging memories devices that ship in production today. This includes an MRAM microcontroller from NXP, a phase change memory microcontroller from ST Microelectronics, and ferroelectric-based microcontrollers from Texas Instruments and Fujitsu. Now let's take a look at where all this memory technology could go. We're going to do some projections for the future. This chart comes from our most recent report, which is Emerging Memories Takeoff. It shows that the total emerging memory market, MRAM for split across point, could exceed $44 billion by 2031. This chart shows how petabyte shipment growth could drive that number. The figure compares the current and projected capacity shipments for the next 10 years for these emerging memory non-volatile technologies represented by MRAM and 3D XPoint versus DRAM and NAND flash. In summary, NOR flash and SRAM have stopped scaling, DRAM scaling has slowed. There's new non-volatile memory types available which will fill that void and allow continued scaling. They will also lead to new memory-centric computing architectures. They will change the memory and storage hierarchy. There's 4 leading candidates for these new memories: MRAM, phase change memory, resistive RAM, and ferroelectric RAM. Leading foundries already support these new memories, and they're in use today. And MRAM and phase change memory revenues in particular, we project to exceed $44 billion by 2031. Now this data comes from, much of the data in this presentation comes from a report that Jim Handy and I have done. We just recently updated it. Emerging Memory Reports, Emerging Memories Takeoff is the latest report. Describes the entire emerging memory ecosystem, all these technologies, the companies, the markets, support requirements. We forecast emerging memory consumption both for embedded and discrete devices. It's 230 pages with 36 tables and 155 figures, and these URLs at the bottom of the slide allow you to learn more about these reports. So here's some references that might be useful to you folks. And I want to thank you very much for listening to my session. And just a reminder to take a moment to rate this session. And I look forward to talking to you.